Hello, everyone. Thank you so much for joining us today for a guest speaker session at Web for AI. We have with us Ziqi Wang, who is a PhD student at UIUC, advised by Professor Heng and Professor Wang, and he's working on AI reasoning. Previously, he was intern at Meta GNAI in 2024 summer, working with Louis Wang, and spent 2 summers at Google working with Dr. Frick Wu and Dr. Li Ho. Today, he will be presenting his latest research on teaching language models to self-improve by reinforcement learning. Thank you so much, Vicky, for your time, and I will pass it over to you.
Yeah, and thanks for the introduction. So yeah, I'm a first year PhD student. I'm gonna now, work on the reasoning from the RL perspective. And thank you for taking your time attending this talk, especially a few hours ago is iClear deadline. So perhaps some of you are working hard on that. And this work is actually done during last summer and it's published in this year's iClear. The paper is actually published 1 year ago, but I hope to talk about this paper in a different new angle, especially nowadays people are more care about like reinforcement learning for reasoning, some reward shaping and process supervisions. And especially like recently, like the OpenAI one that has explicitly addressed that they use RL to teach models to self-refine. So I think these topics may be interesting for some of you. I think if you have any questions, just feel free to interrupt me, and I will start now. So the topic of this talk is to teach LLMs to self-improve by RL. So there are two keywords here. The one is called self-improve, and the other one is called RL. So let's start from the self-improve. So what is self-improve? The most intuitive definition is that I have input, I send it to the model M, and I let the model M to refine, to ask it to refine the answers. And to do so, I will probably collect some self-feedback and put this feedback to the model itself and let the models to refine the answers and repeat this loop so that models can gradually self-revise its answers, and we can get some better quality answers after multi turns of revision. But when speaking of this kind of self-improve, let's start from the simplest one implementations. It's just like prompting, right? Because when you look at the loop, it's basically just we get some self-feedback, and then we send this self-feedback to the models, and we can hope models can refine the answers. So probably we can use prompting. So can you reflect your response and improve it? So models will probably just give some self-feedback and revise the answers. But this kind of prompting method, though it's very easy, it actually faces many drawbacks. Because here, the word improve is very vague, and its definition actually varies depending on the scenarios you are working with. For example, is the improve means to be more helpful? Is that means the tone to be more formal? And do we want to have a more objective answer or more subjective answers, so on and so forth? And even if you directly say that can your response be more helpful, it's still very hard to let the models know what directions you want models to revise. For example, here the helpful could be like more polite to contain more details, or sometimes you want it to avoid irrelevant informations, or you want it to avoid answering dangerous questions. So it's really hard for us to write a concept and a complete rubric to describe what the self-improvement direction is. So this is one of the drawbacks of the prompting. And to summarize, is actually we can use ambiguity to describe the drawback of the prompting methods. And here is the examples. So I prompted these models on POM2. Basically, I asked the POM2 what is the origin of the name Black Friday. And initially, the POM2 answers pretty well. It says, okay, the Black Friday because of the increased profits they experienced. And then I say, could you reflect your response and give a more helpful response to the questions? Or the prompt 2, add some new sentences. But it turns out that these new sentences are just very distracting. They are irrelevant to my questions, which is just the right part of these sentences. And actually, when we really inspect and read the revised answer, is the performance actually become worse. So the prompting methods may just not function as we expect, because what model understand helpful and what we want the models to be may have some disagreement. But this is actually one of the small problem of the prompting. The more serious problem is that the prompting method, it just doesn't work. It just doesn't work. And no matter, and even if you can just precisely describe your needs, it just doesn't work. And for example, if we let the models to self-refine the answers, so that we hope models can correct their reasoning paths, and hopefully they can just do better in the math problems, then we find that most of the time, for example, you can look at this figure. The models will turns out to revise the correct answer into the incorrect one, which is denoted by the red color. And yes, sometimes the model will just revise the answer so that the answer will come from will be correct from incorrect ones. But if you look at a portion, there's still a large portion that the model will just make the correct one into incorrect. So it just doesn't work. So that's why we think that the prompting method for the self-improvements may not suffice. And that's why what we want to do here is to teach LLMs to self-improve by RL. It's not just prompting, because we think prompting has its own bottlenecks. So when we say RL, yes, we are referring to some like the reinforcement learning from from human feedback. But the key thing is that we need to understand what is reinforcement learning from human feedback. So I believe some of you may be very familiar with this, but in case someone do not really know the reinforcement learning from the human feedback, I will just give a quick recap here. So basically speaking, when we conduct RLHF, we first have a language model, or we call policy model in RL's terminologies. And we first have some questions like prompts, and we send these prompts to language models, and we can get some answers. And after we get these answers, we also have another model called reward model, and we put the question and answer together into the reward model, and the reward model should give us a reward. And this reward reflects the quality of this answer. So if the answer is of a good quality, then reward is high. Otherwise, the reward is low. And this reward will be used to update the language model using some RL algorithm like policy gradient, PPO, or reinforce, or so on and so forth. But mostly now people will use like PPO because it's just widely used. Well, so in this kind of pipelines, what we need is actually a language model, and surely we'll get this, and some human collected questions and a reward model. But how we get this reward model? So in the RLHF pipeline, we have one more step is called the reward modeling. We need to train a reward model. But how to train this reward model? We typically speaking, we still have a question, a human collected prompts, and also two annotated answers. They are all aimed to answer these questions, but one has a better quality and one has a worse qualities. And we let the human to annotate these two responses, and the human can annotate which one is the chosen answers and which one is the rejected answers, and we can get these response pairs. And we send these response pairs to the reward models, and for each response, the reward model will output a reward. And this reward, will will be used to train the reward model. So the reward model is trained to assign a high reward to the chosen answer and a low reward to the rejected answers. So this is how the reward model is training. And once we have this reward model, we can just put it into our RLHF pipeline, and we can get a language model that is reinforced through reinforcement learning. Yes, and when we look at these reinforcement learning pipelines, we can find that the reinforcement learning actually teach LLMs to generate a good response, right? Because LLMs are optimized through RL to generate an answer that can have a high reward. But the don'ts is that the LLMs do not really learn to revise the response because all the input and output is just a question and an answer. The LLMs is not learned to, okay, I need to revise an already existing responses. So this is not learned by LLMs. So in order to empower LLMs with these revision capabilities, we have to modify the reinforcement learning pipeline a little bit. So this is just comes to our approach. So the reinforcement learning, we need to always remember that our goal is to teach models to revise answers. So our input is not just a question itself, but we have a questions and we have an already existing answers. We send these LLMs, and we send these kind of inputs to the LLMs, and we let the LLMs to decode a better response. Well, ideally, we hope this is a better one. And after we get this, after we get this decoded a better response, we send the questions, the reference answers, and the decoded hopefully a better answers to the reward model, and the reward model hopefully should or we need to train a reward model that directly model the reward gap between these two answers. And after we get this reward gap, we still conduct an RL algorithm like PPO. So the difference between this RL cycle and the previous one, I just introduced, is that in these ones we directly model the reward gap between the two answers, and after the RL, our language model should be able to learn to generate a better response based on the reference response. So this RL pipeline seems like very straightforward, but if we look into deeper, we find that we need to tackle some new challenges. The first one is that we say that we need to have a reference response as an input, but where this reference answer should come from, right? Because typically speaking, in the RL, we only need to correct questions, and the answer is all obtained by the language models. But now we also need to prepare a reference to answers. And another thing we need to care about is that here we want the reward model to directly model the reward gap between two answers. But in the original reward models, actually the original reward model will just give a reward based on a single response. It's not a response pair. So we need to change both the reward modeling and this input and find a way to obtain this kind of reference answer. So let's first look into the reward gap modeling. Because our goal is to model the reward gap between two answers, and the most intuitive thought is that can we just use conventional reward model? Because yes, we have a response pairs. I can just let the reward model to give two scalar reward of them, and I just use a simple subtraction, so I can model the reward gap. Well, it actually seems very promising and very simple. It seems like we don't need to change the reward model at all. But unfortunately, it turns out this kind of solutions just doesn't work. This is because the reward model is not well calibrated. And for example, if your reward model have a reward range from 0 to 10, and if the one response get a reward of 9 and one response get a reward of 0, then you can say, okay, perhaps their reward gap is 9. But now, if the two response, one get a reward of 9 and one get a reward of 8, then the reward model is not well calibrated. So the response that get a reward 8 doesn't necessarily to be worse than the response that get a reward 9. And specifically, if we look at this paragraph, if we look at this figure, which is presented in the Anthropics paper, so they actually show that, okay, so if the two responses all has a very high reward, so which means the x-axis becomes very large, then if you use this reward model to classify which one is better, then the accuracy will drop. So which means if both response have a very high reward, then the absolute scalar of these two response, the absolute scalar reward of the two responses cannot be really a fair judge to tell which one is better. So we still need to directly model the reward gap because this is unreliable. So that's why we think we need to go beyond the reward model and we need to directly train a preference model. And here the preference model is that we take a response pair and we directly output the reward gap between two responses. So in this way, we don't need to get two separate reward and do some subtraction because that's unreliable. But the question here is that how can we train this preference model? Because previously the reward model can just be simply trained by putting the chosen answer have a higher reward and the rejected answer a lower reward. So in this paper we propose to train this preference model in a very different way. So we observe that the reward gap between the chosen answer and the rejected answer should at least be large than the reward gap between two identical responses, and should be larger than the reward gap between the rejected answer and the chosen answer. And this is just this should be this inequation should hold everywhere. And based on these observations, we can just train a preference model as pure as a reward model, because we can just say, okay, the reward gap between the chosen answer and the rejected answer should be larger than the reward gap between the chosen answer and the chosen answer, and so on and so forth. So ideally speaking, after we train this kind of preference models, the reward curve should like this. So we have the reward between the winning between the chosen one and the rejected one should have a highest reward, which is this part. And the reward gap between the rejected response and the chosen responses should have the lowest reward, which is this part. And for the reward gap between two identical responses, their reward distribution should be in the middle. It just should be here. And this is perfectly satisfied this inequations. Right. So this is one. So this is just the preference model we train. And after we get these preference models, we can go back and to see. We can go back to see this whole pipeline. So actually, we've already solved this part because we've trained a preference model that can directly model the reward gap. So the last thing that we need to tackle is that okay, in this RL pipeline, how should we get these reference answers? So theoretically speaking, the choice is very simple because we can simply just choose a reference answer that is generated by LLMs itself. So this is because the goal of our RL is to let the models to self-refine its answers. So surely the reference answer should be the answer that's generated by LLMs, so that the training objective and the inference objective are the same. But empirically speaking, this kind of choice may not be an optimal choice. So this is because the RL prompts, this should be neither too easy or too hard. Because if the RL prompts is too easy, then after RL, your model will learn little. But if the RL prompts is too hard, your model is likely cannot sample good answers, so that your RL performance is very bad. So in the RL, we really need to make the RL prompts to be an intermediate level. However, the LLMs generated response are already in a very high quality, which means if we directly use the LLM generated response as a candidate as a reference response, the RL performance will be very bad. For example, if we just do, like as we said, directly apply LLM response, then we can get the reward curve of we can get a reward curve of this. We can get a reward curve of this, and when we look at this reward curve, we can see that at first the starting point is very low, which means at the beginning the LLMs does not know how to self-refine, and after self-refinement, the LLMs will literally generate some worse responses because it falls in this range. And even after we use RL to teach models to generate better responses, it finally ends up to generate some similar responses, either identical or some similar quality responses. So that's why we say that this is not a good option, because it's too hard for models to learn. And on the contrary, if we can first use some worse responses or some low quality responses as a reference response, and then switch to LLM responses, we can get a far more better optimization curves. Because after we use some worse responses and reference responses, we use this to do RL. We can get a very, very high, very good starting point. And after we go into the RL, we can see the model will achieve a very high reward range and fall into the better range, which means after this cycle of RL, the models is able to generate the better responses, is able to learn self-refinement based on its own outputs. So this is another lesson we need to learn, is about how do we choose the reference answers. But in short, is basically saying we should first choose some low quality reference response and then use LLM generated response. So after we solve this two part, we can just start training, and we can train a model. We can use reinforcement learning to train a model and get a model that learns how to self-refine. So during inference, actually, things is more straightforward. We can first let the language models to generate an initial answers, and then we put these answers into the input and let the models to generate a better answers. Because this model has already experienced the reinforcement learning, so it should generate a better responses. And this process could be done iteratively, which means in the next round, I can put these better answers to the input again, and hopefully our language models can revise this further and get an even better responses. So this is about the inference strategies. So after this training and the inference, we ideally should have a language model that knows how to self-refine. And this is about the method approach. So in the next, I will just introduce some experiment settings. So the first is that in the previous presentation, I never introduced the name of our method, but now I just want to give the abbreviations. It's called PIT. And in the data set, we actually choose 3 data sets. One is called anthropic RLHF, and this data set is designed to train models to generate helpful and harmless responses. And another data set is OpenAI's summary data set, which is designed to train models to generate comprehensive summaries. And at last, we also generate some synthetic data. And this synthetic data is actually instruction following data set that contains many constraints, and we see how good the models can follow instructions. And for the evaluator, we actually choose 3 evaluators. One is GPT-based evaluations, which needs carefully designed prompts, and another is called the reward models. We use a reward model as the evaluator, but the reward model actually face a problem about reward hacking, so it is not reliable too. And at last, we introduce human evaluation, which we believe is the most robust evaluator. And when the GPT-4 and the reward model disagree with each other, we will let human evaluation involved. So here's the main experiment of our method. So the first I want to introduce is that what this comparison means. So the original means the first time generation of the LLMs, which you can say is that I just directly prompt LLMs and obtain an initial response by LLMs. And here's why the win means the annotated chosen responses provided by the data. So the first comparison actually reviews how good is the LLM response compared with the chosen response in the data. And this comparison has nothing to do with our method, and it's just to give the readers a sense of the LLM's base capabilities. And the next is called the PIT original, which means we apply our self-refinement method on the original response and get a better response. And we compare this revised response versus with the original response. And similarly, the self-refine here is just the prompting approach I mentioned at the beginning of the talk. And we see, okay, if self-refinement can improve the response too. And at last, we compare our method and self-refinement to see, even if like 2 methods all improve the response qualities, which one improve more? So this is about the 4 comparisons. So here are some takeaway message of these tables. The first is that the PIT improves the LLM response because in the GPT-4 evaluation, in the reward model evaluations, we can see the winning rate of our PIT response is always better than the original response. And the second is that the self-refine improves the LLM response too. And the third one is that our method actually performs better than self-refine. That means even if even though PIT and self-refine they all improve the LLM response, our method actually performs better than the self-refinement. So this is the main experiments. So this is the main experiments, and which is pretty as expected because it's just our goal and it's just our motivation to develop this kind of method. But still, I hope to show some more interesting result here. Is that in the previous slides, I showed that we can use this self-improvement iteratively, and it seems like we can just improve the model response qualities in each iterations. But it turns out this is not the case. And for example, after I have the original responses, I can use self-refinement to refine several iterations, and so can I use my my method to improve several iterations. And we can see that it's not saying that the more iterations will lead to a better qualities, because in this table we can see the fourth iteration is better than the first iterations, is better than the fifth iterations, and it's better than the third and second iterations. So that means that even if we use RL or we use prompting to let the models to self-refine, it doesn't mean like each iteration will have a better will have improvement guarantees. So this is actually an unsolvable problem. Like, when should we stop the iterations, and how can we guarantee that the response quality is at least not decreasing? So this is just the main content of this paper. But if you look at the recent progress of the RL community, you can see there are some opportunities here in the futures. The first is about the power of the curriculum RL. So in the previous slides, I showed that we actually need to choose a weaker reference response at the beginning, and then we put the stronger reference response so that we can make our RL more successful. And if you look at the recent Chairman 2.5 math report, they actually have a very similar findings, and they find that only keep intermediate level problems in RL actually led to a better result. So what they do is that they sample 8 responses per problem, and if they find that more than 5 out of 8 responses are correct, then they think this problem is too easy. Otherwise, if there are less than 2 out of 8 responses are correct, they think these responses are too hard. And by this, they can just filter out some too easy or too hard problems and keep some intermediate level problems and use this into RL, and they can get a very good results. So we think the curriculum RL is still a very promising way for the future research directions, especially when RL plays a vital role in the reasoning and self-refinement. And another opportunity is like the reward modeling. So the reward modeling is that the preference model training signals introduced in our paper is still a very preliminary ones. So there should be some better training signals that deserves us to have more investigations. And some more about the reward modeling is that, can we just go from the reward that is simply output a reward based on the generated response to verifier, that is to compare the generated response with some oracle responses. And also can we use some multi-turn reward shaping, which means when we are using when we want to do self-refinement, our ultimate goal is to let the models to generate response as good as possible for example in turn iterations. So all we care is about the last iterations, the result of the last iterations. But actually, we can give some reward signal to give some reward signals in the intermediate iterations too, and which is called reward shaping. So overall, like when we want to use RL to do the self-refinements, there's still a lot of opportunities, and there's still many research questions that is unsolved right now, and we think is pretty promising to investigate this in the futures. So at last, I just want to give a quick conclusion of this work. So basically, we hope that I hope I clearly illustrate the method and the achievement. So the achievement is that we propose self-improvement model by using RL, and the method is actually to reformulate the whole RLHF pipelines. They are typically like the two contributions. The first contribution is that we go beyond the reward model and to train a preference model instead, which can have more robust reward gap estimations. And the second is that we go from single response optimizations to response pair optimizations. And specifically, we also adopted the curriculum RL to make the response pair optimization more successful. And I think that's all the main content of this talk, and pretty much thanks for people that you attend these meetings. Especially this just several hours ago. It's just a clear deadline. So if you have questions, and just feel free to ask. And otherwise, I think that's just the main content of this talk. And thank you very much.
I have a question. Can you hear me? Hello. Hello. Can you hear me?
Yeah, I can.
Yeah. So in this paper, you were kind of trying to you have shown an iterative improvement, like gradually refinement there. So how does it compare with the process supervised reward models? So are there any connections? Your approach shown improvement, but the self-refine doesn't work. So is there any deeper connection there with process supervision and your approach?
Yeah, I think that's a good question. So the process supervision model is more like, so I have a response, and uh, and and previously when we doing conventional RL, so let's say okay. So let me just go back to that slides. So conventional RL is saying that we have yes, so we have a response and we get a reward model, get a reward and PPO. So the process supervision is that suppose my answer have 6 tokens, then the conventional RL will assign all rewards to the last token and all the other tokens 0 reward. So the process supervision is to change this paradigm so that they hope to give some credit assignment to some middle tokens. So for example, the first 5 tokens, they have some reward and it's not just a 0. So the process supervision models could accelerate the convergence, and in practical will often lead to a better optimized result. But in our models, but like in our proposed approach, we are more clear about the multi-turn. So that is for the first turn. For the first turn, I get answers, and I let a model to generate revised answers, and I want to optimize so that each turn will get a better response. So it's basically the task we are focusing on different. So in our task, we still use outcome reward model. We do not use process supervisions. However, we use our reward model in a multi-turn tasks. So that's the difference. So yeah, I hope I clearly illustrate this.
Yeah, thanks. Thanks.
Can I have a question?
Yep, sure.
Yeah. Not sure if I missed this, but can you explain again how you prompt the language model to generate a better answer from the question in the previous answer?
Oh yeah, yeah. I think that's a good question. I think I didn't mention this in my talk. So like in my implementations, the question and the answer are inserted with a special token. So okay, so let me tell you. So this is a special. So here there is a special token here, and there should also a special token here. Special token. That means there is not there's no natural language prompt here. So the reason I do not use natural language prompt is because this is a training process. So there's not necessary to be a prompting. But yes, if you could have some prompting, that should be better. Yeah. But it's it's just not necessary. And if you are interested, you can look at this paper. I think I have at least one paper here. You can look at this paper, which just come out recently, and they actually insert some natural language prompts between the answer and a revised answer.
I see. It's interesting. It's interesting how we didn't use any prompt to tell the model to generate like a better answer, but it's still able to generate like a different and probably a better answer. But yeah, thank you.
Yes, thank you for your suggestions. I think it's a good question. And if you are interested, you can give it a try. But I haven't tried that yet.
I actually have another question. Can you re-explain the results, like the table?
Yep.
Yeah, I didn't understand like the numbers. For example, on the GPT-4 column, like the first one would be win rate, the second would be lose rate, and the third one would be the difference. But whose win rate and whose lose rate? Like I didn't really understand.
Oh yeah. Oh, okay. So and for example, for the self-refined versus original, so we basically compare self-refined and original. Here, the win rate means the win rate of the self-refinement, and the lose rate means the lose rate of the self-refinement. So it's always the win and lose rate of the first term.
I see.
Yeah.
Thank you.
You're welcome.
If we don't have any other question, we can conclude the talk here. Thank you so much, Vicky, for your time. It was really insightful session.
Yeah. Thank you all for your time. It's pretty happy that I can present here.
Thanks everyone.
Thank you everyone.